Hello everyone. Welcome to the live section of this course, which is Foundation of Classical Electrodynamics. Let me give a brief introduction about myself. I'm Gitanjali I'm a research scholar from IIT Delhi, and I'm the TA for this course. So, as I said in my previous live session, we'll go through the concept that has been taught during this week, and we'll solve the problems that is related to this weekly content. So now we are in week 9, and in week 9, if you recall, we basically saw what is the distribution of electric field in a polarized object. So for a polarized object, you saw if you have a polarized object, then you can have the two types of charges. One is the surface bound charge, and the another one is the volume bound charge density. And this bound charge density they contribute to the total potential, and you can get the potential if you take if you integrate the contribution from the surface charge density as well as the volume charge density, and from that you can calculate the potential. Then you can also calculate the other parameters such as electric field, total charge, or any other parameter you want to calculate. So we look at this, and we saw how to calculate the displacement vector for a polarized for a dielectric object, and we saw that it's quite related to what we have seen in our previous classes. So only the difference is that the electric field will be replaced by the dielectric dielectric vector, which is D. So previously we had E dot ds is for Gauss law. We have seen is E dot ds is q enclosed by epsilon naught. And for this, you will get D dot ds is q free. So for electric field, it's the contribution from the total charge, but for the displacement vector, it will be the contribution from the free charge only. And other relations are quite same, similar to what we have seen before. Only the uh, total charge will be replaced by the free charge, or total charge density will be replaced by the free charge density, and E will be replaced by the D vector. And besides that, we see, so first we have seen the electric fields in matter. So how we can, and the different relation also, I think you can easily uh, recall what were the relation of displacement vector with the polarization, and for a linear dielectric, what is the relation between the polarization and the electric field, which is nothing but P is epsilon chi E. E. This is for linear. For nonlinear material, we'll have higher order term like 2 e square like that. So we are not considering this a nonlinear term. We are focusing on what is the behavior of a linear material, and from that we see one of the special case of how to find out the potential for a specific type of configuration. Like if the potential is given, if the potential is zero in some region, and if it is satisfying the Laplacian equation. Then you can also, for this simple case, we can follow a procedure to find out how we can solve the Laplacian equation to find out the potential, then electric field, then the surface charge density. Or you can also choose, we also see the method of images, which is only applicable whenever we have a grounded conducting plane, and there is a charge sitting on this plane. Then from for that complicated configuration, you can follow the method of images to calculate the potential, then force, then the surface charge density. So we'll look at the different types of numerical problems on this. Also the problems on solving the Laplacian equation using this formulation. So let's start solving our first problem. So first problem is based on the capacitor. So it's quite simple. If you know the relation, you can easily find out what will be the answer for this question. So let me read out the question. There are two parallel plate capacitor which are separated by a distance x and 1.1x. So let me draw it. So there is two capacitors. This is D1, which is x, and this is D2, which is 1.1x. So for this configuration, it's also given they have a dielectric material of dielectric constant 3. So this epsilon is 3. Here is also epsilon is 3. Inserted between the plates of the capacitor and connected to a battery of voltage V. So you need to find out what is the difference in the charge of the second capacitor compared to the first one. There are four options. One is 7%, 15%, -9%, and -33%. So let me calculate it. So for first one, you can easily guess the charge accumulated will be C1V. So both are connected to a battery of same voltage. So Q1 will be C1V and Q2 will be C2V. And C1, if you recall, it's nothing but epsilon naught, epsilon R A by D1 V. And Q2, for Q2, it is epsilon naught, epsilon AV by D2. So D1, D2 is already given. One is X, one is 1.1X. So is the screen visible? I forgot to ask. And the voice is, it's fine from my side, right? Okay. So D1 it is given. So if you take the ratio Q1 by Q2, it will be nothing but D2 by D1. Or so we need to find out second with respect to first. Let us take the ratio of Q2 over Q1. So this will be D1 by D2. So D1 is given X, D2 is 1.1X. So this is 10 by 11. Now we need to calculate the percentage, the difference in the charge. So for this you can you can take Q1 minus Q2 by Q1, and it will be -1 by 10 for 11. So this is what we want to calculate it. So delta Q over Q1, to take the percentage, it will be 100 by 11, which is nothing but -9%. So answer will be option C. Okay, so I hope this problem is clear to you. Let us move to our next problem. So first we'll see some basics problem which is totally based on the formula. Then we'll slowly move to our more complicated problem. Okay. Second question, it's given. There is a unit cube made up of dielectric material. It has a polarization. Polarization is given is CIK plus 4JK. The edges of cube are parallel to the Cartesian axis. Find the surface charge magnitude on the surface parallel to the YZ plane at x equal to 1. So this is based on the direct formula for the surface charge density. So please calculate it first and let me know what will be the answer. So you need to find out what is sigma b given the P is this. There are four options. Option A is plus 3 units, option B is minus 3 units, C is plus 4 units, and D is minus 4 units. Calculate it and let me know the answer. Yes, it's option A. Good. So sigma B is P dot N K and N K is for YZ plane. So if you have a YZ plane or a cube, the normal vector is in the x direction, right? So it's given in x equal to 1, so it is positive ik. So if you take the dot product, it will give plus 3 units. Option A. Okay, so let us move to question number 3. Similar to question number 2, but here you need to calculate the volume charge density as well as the surface charge density. So there is a dielectric cylinder of radius A which has a polarization P is given by beta or R cap. Beta is a constant, R is the distance from the axis of the cylinder, and you need to calculate what is the surface charge density and the volume charge density. Recall what will be the formula for rho B and sigma B, and let me know the answer. For cylindrical coordinate, recall what is the formula for divergence, call, or gradient. Use that standard notation to find out the answer. First, try to calculate sigma b because it's easy to find out sigma b. Then you can see whether the sigma b is falling to either A or B or C or D. So if it is not falling to either of these, the answer will be obviously D. But if it is falling to sigma B, sorry, C option, then for that case, you don't need to find out rho B because only this C option has sigma B is beta pi A. But if it is beta A, for that case, you need to find out rho B also. So first calculate sigma B, check either whether C or D is the answer. If C or D is not the answer, then you need to calculate rho B for that case. So sigma B, you can easily find out this is nothing but P dot n cap, right? For a cylinder, what will be the n cap? Option D, because both surface charge density, volume charge density are equal and opposite. Okay, so let me calculate it first. So P dot n cap, I think, and you need to calculate the surface charge density at the surface. So that means it is equal to A. So beta, this is beta R cap, or you can write it as, okay, so let's take this is R equal to A. So beta R cap and cap is R cap at R equal to A, which is beta A. So we know surface charge density will be beta A. For volume charge density, it is nothing but minus of divergence of P. And if we recall the for the cylindrical coordinate, we have the divergence formula. This is 1 by S or 1 by R, dou by dou R, P, P is beta R. So this is minus 1 by R, dou R of beta R squared, which will give minus 2 beta, right? So here you can easily see it is minus 2 beta and this is beta A. So that means the answer will be option A. Please verify your steps it's whether the solution is fine for you, or if you have any doubt, let me know. Dinakar, is it okay with you, the solutions? Yes, we are considering the curved surface because if you recall, when we're trying to calculate the electric field also, we are trying to take the curved surface. So we didn't consider the age effect. So we are, for time being, we are ignoring the age effect. Any other doubt? So it's like the electric field is radially outward. So that's why we are considering the curved surface. Um, None of the above, the trick one, because if you consider a cylinder, so whenever, let me think, somewhat also depends if you look at in more details. This one, both surface charge density and volume charge density are equal in opposite. No, if you see here, it is beta and it is minus 2 beta. If you don't consider the H1, so it's totally different. And if you, okay, so I think you got confused about the total charge. So if you take the total integration of, sigma B and rho B, it should give 0. I think you were talking about that. That concept is always true because, but it's not like rho B and sigma B will be equal. It's like the total charge should be 0. Total, if when you take the integration, the total charge should cancel with each other. That's why we have a negative charge here and a positive here. Okay, so let's do one thing. Um, if you take the total charge of the outer surface, what it will be? Sigma B is beta A, and the outer surface area is 2 pi A, right? 2 pi AL. This is total charge. And for this is sigma rho B dV. So 2 beta and the surface, okay, total volume would be pi a square L, I think so. You can see pi a square L. Okay, you can say these two are equal. So total charge should be equal. They should cancel, but it doesn't mean the total charge density should be equal. You were right in conceptual wise because the material was neutral before. So whenever you apply electric field, it get polarized because of the dipole separation, because of the formation of total dipoles, and because the material was neutral before, so total charge density should be total the bound charge density should add up to 0. So the charges are opposite. Yes, the charges should have opposite sign, but the charge density values should be uh, not like they are equal, but the total charge should be equal and opposite. So I think it's clear for you now. Okay. So the next problem, it's quite similar to what we seen in question number 3. So there is a sphere of radius r which carries a polarization p, which is kr, where k is a constant, r is the distance from the center. Calculate the bound charges sigma b and rho b, and calculate the field inside and outside the sphere. So let me calculate. So sigma b is p dot nk, and be careful while calculating the sigma b because always put the boundary values while calculating the sigma b. For this, we are calculating at the boundary surface of this sphere. So that is why r should be equal to capital R. So p is k r and kp is r unit vector at r equal to r. So this will give kr. And rho b, this is minus of divergence of p. And for a sphere, we have minus 1 by r square, dou by dou r square, p is kr. So 1 by r square, dou by dou r, kr cube. This will give minus of 3k. So this is the surface bound charge, this is the volume bound charge. Now let us calculate the field. For field, let's say we are trying to find it in the region r less than r. So for that, you can use the Gauss law. So E dot ds is Q enclosed by epsilon naught. Here Q enclosed is the total charge. the charge would be bound charge or free charge. But because the free charge information is not given to us, we can take this is Q bound. And for R less than R, so we are looking at the volume. So there is no surface charge. So that is why Q enclosed it will be the integration of rho d dv. And rho d is given minus 3k. dv is r square sin theta d theta d phi. Integration. So this will give minus 3k 4 pi r square. And there will be 3 here. 4 by 3 pi r cube. Okay. So Q enclosed will be minus 4 pi kr. We know Q enclosed. On what basis we consider unit vector and cap depending on the inner outer surface is values given. Okay, so now we were talking here. Let me given one example. So if you have a solid sphere, so the unit vector you can easily guess this will be outward only. So here the unit vector is r cap, right? But when you have a hollow sphere, or sorry, when you have a two sphere where the inner one is this is point and this doesn't have any volume, let's say it's a metal or it is surrounded by a dielectric. So for this we have two surface, one is here and one is here. So for outer surface it is radially outward, right? But for the inner surface, this is the normal vector is in minus r cap direction. Okay, let me clarify the doubts one by one. For Dinakar, I hope it's clear now. So whenever you have a two surface, so the normal should be normal to the surface and away from the volume, right? So for the first case, it's normal to the surface and away from the volume. And for the second one, if you consider there are two surfaces, outer one it is NK, but for the inner one, if you take this one, so it is pointing towards the volume of the sphere. So that is why we can't take this as normal. So always take a normal vector which is away from the volume and normal to the surface. Um, okay. So what I'm trying to say, you have two surfaces here. So, and there is some dielectric. So this is the volume of this system. This is the volume. You can take this is a coaxial cable or whatever you want. So for this case, you can see there is a inner surface and there is a outer surface. This is the outer surface. So normal vector by definition, it means it should be normal to the surface and should point away from the volume. So for this surface, that's why we take this direction, not this direction. So this is pointing towards the volume. So that is why for the outer surface, we have NK is positive r cap. This is the r cap direction, right, for the spherical coordinate. If you recall r theta phi, For r cap, this is the positive r cap direction, this is the positive theta cap direction, and this is the positive phi cap direction. Okay. And for the inner surface, what will be the normal now? It should be like this, not like this, because it is pointing towards the volume. So it can't be normal to the surface. So that is why we have taken n cap is minus r cap. Why is that so? Okay. So it's quite related to the field produced by this surface charge. So um, what you can say, let me think. One is it's by definition we are treating the normal vector like this, and the other physical reason is A dot n cap. Yeah, you can take it like that towards the charge free region. That can be one of the explanation that you can take. Or let me think about it. Is there any physical reason behind this? Maybe I think it's related to the field. So that is why we are taking like this. But for right now, I don't remember the exact reason. So let me think and I will let me tell you in the next live session. But uh, other than that, if is it clear how we can take the unit vector for the different type of surfaces if you are given a random surface? Let me tell you the reason in the next class. I think it's related to the field, but not able to recall the exact reason. Okay, for 60, free charge, it's like the question should explicitly say that there is a free charge. So if it is doesn't saying it's there is a free charge, then consider free charge is zero, because here also you can see there is no free charge. Unless and until it's a metal, you can't guess whether there is a free charge or not, because dielectric doesn't have any free charge unless and until you put some free charge from outside. For that case, the question there in the question it will be explicitly written that some amount of free charge is loaded on the surface. Okay. And if it is not given in the question, then don't take the free charge contribution or only take the bound charge contribution. Okay, for the dielectric case. But if it is given it's a metal, then for that case, you can easily guess there will be a free charge, which is the charge on the metal surface. So, is it clear now, Srishti? We were here, I think. Okay. So, we're trying to calculate what is the field. So as I said, Q free was not given, so we take the contribution from Q bound. And if you consider a reason for R less than capital R, so there is only volume charge here. So that is why I have taken contribution from rho B. And just take the integration, you will get minus 45 KRQ. So we know the charge now. So E dot ds will give. So whenever you are taking E dot ds, remember that Q enclosed is Q free as well as Q bound. And because Q bound is zero, Q free is zero, so that is why we are taking the contribution from Q bound. So it's now easy for you. It is E 4 pi r square, and the right hand side we have 4 pi ARQ by epsilon naught. So 4 pi will cancel, 1 r cancel. So E is minus k r vector by epsilon naught. This is the field that will be induced inside the sphere, dielectric sphere. And for the outside, we have both surface charge. So whenever we're considering a outside Gaussian surface, there is sigma b sitting here and there is rho b sitting inside the volume. So that is why Q enclosed will be rho v dv plus sigma b d. Rho b dv we have already calculated it. And the integration from rho v dv will now from 0 to capital R. Theta and pi integration is as usual, 0 to 2 pi and 0 to pi. So this will give minus 4 pi k capital R cube. And for sigma b dA, remember that sigma b is the surface charge density at the surface. So that is why we'll take, sorry, this will be double integration. Sigma b we have calculated. This is kr, and the area vector is in the radial direction, which is 4 pi r square, right? Okay, I have already taken the integration, but in general notation, it is r square sin theta d theta d phi. One is 4 pi kr cube. This is 4 pi kr. So you can see this is cancelling. So electric field would be 0 for outside. So this is based on the question you have asked in question number 4. So it has two types of surfaces. There is a thick spherical cell. One is one is radius A, other one is radius B. Outer radius is B, inner radius is A. So this is A, and the outer radius is B. And there is a Trojan in polarization. So this is polarized and it is given P is P by R, K, where K is the constant and R is the distance from the center. There is no free charge, Q free is 0. Calculate the bound charge in all three regions and calculate the displacement vector and the electric field vector. So for now, sigma b, it is because it is both inner surface as well as outer surface. So this has two contribution. One is P dot nk at r equal to A, and another one is P dot nk at r equal to B. P is K by r k dot. For the inner one, it is negative r k in this direction, and for the outer one, it is positive r k. Minus r k at r equal to A, and this is K by r k at r equal to B. So this will give minus K by A, and this will give K by B. And rho B is minus of divergence of P. And for spherical one, we have 1 by r square, dou by dou r squared, PR, which is K by R. So this is minus K by R squared. So we've calculated the charge density. Now we'll see the displacement vector. For D, it is given there is no free charge. So you can take D dot ds is Q free, which is 0. So that means, and it is valid for every reason. So that is why D is 0 everywhere because there is no Q free charge. Let us see the electric field now. If you recall, D is nothing but epsilon naught E plus P. This is the relation we had seen before in the class. So for R less than A, so whenever you are considering this reason, so there is no Frozen in polarization, right? So that means P is 0 here. So for R less than A, P is 0. So if you put it here, D is already 0, so that means E is 0 for R less than A. For in between reason, we have a Frozen in polarization, which is given K by R. So this reason, there is a polarization P K by R R K. So P is K by R R K. So that is why E will be, so epsilon naught P is 0. So E will be minus P by epsilon naught, and P is K R K by epsilon naught R. So we have a field like this in between the region, and for R greater than B. So here, so if you take a Gaussian surface here also there is no polarization, and D is 0 already. So that is why electric field also 0 here. Okay. So electric field is 0 when R less than A, and it is K by epsilon R, RK for ARB, and it is 0 when R greater than B. Okay, so is this problem clear to you? Okay, so let us see our next problem. So there is a spherical conductor of radius A which carries a charge Q, and it is surrounded by a linear dielectric material of susceptibility chi e out to a radius P. Find the energy of this configuration. So you have a conductor and it is surrounded by a dielectric. There is a charge, the charge Q here. This is susceptibility chi e. This one is A, this is B. Linear material of susceptibility chi e, and find the energy of this configuration. So if you recall, energy is nothing but epsilon by 2 E square dV. So this we have seen before. But whenever you have a dielectric, the configuration energy of this configuration will be epsilon by 2. Sorry, we have to absorb the epsilon. This is d dot e dv. And when there is no dielectric, you can replace this as epsilon e. This will give back this equation. This is the more general form of integration of d dot e dv. So our task is to find out d, e, then integrate it over all the region to find out the energy. So let us calculate d and e first. For d, all you need is Q free charge. So whenever considering R is less than A, there is no free charge because it's a metal, it's a conductor. So Q free is 0, that means D is 0. And when you consider R is greater than A, Q free is Q. For all the reason outside R greater than A, total free charge is Q. So that is why the displacement vector will be same in all the reason. In the region where R greater than A, so D would be, so D dot D is Q. It will give D is Q by 4 pi R square. R T. Okay. Now for E, this is same, you need to take E dot ds is Q enclosed by epsilon naught. Or one thing you can do, because your Q bound is not given, because polarization is also not given. So that is why you can also see in the problem it's given, it's a linear dielectric material of susceptibility chi E. So for linear dielectric, you can see D will be epsilon naught E plus P, and for linear material you can write P as epsilon naught chi E, which will give this is epsilon E. So that means if you know D, you can calculate what will be E. So E will be D by epsilon. Okay, so now we have D is 0 for R less than A, and it is Q R K by 4 pi R square for R greater than A. So electric field will be, it is 0 for R less than A, D by epsilon. So this will give Q R K by 4 pi epsilon R square for A R B. So the reason why I'm considering this reason, because chi E is only valid, chi is only there in this ARB region. Outside there is no material of linear dielectric. So that is why this will be Q by 4 pi epsilon R square in between the region. Outside it will be only epsilon naught, because P is 0 outside, right? If you put P is 0 here, D E will be D by epsilon naught. So that is why this will be Q R K 4 pi epsilon naught R square for R greater than B. So is this calculation clear? Now we know both D and E. Now it's quite easy to calculate what will be the value for this integration. Energy, it is half d dot E dV, half inside for this region, this is 0. And for A or B, if you consider this region, so Q by 4 pi square 1 by epsilon naught, epsilon A to B, and 1 by r square, 1 by r square, it will give 1 by r to the power 4. dV is 4 pi r square dr. And for r greater than b, we have 1 by epsilon naught q by 4 pi r square 0 to infinity 1 by r to the 4 pi r square dr. So let us simplify it further. This is 1 by epsilon q square by 4 pi. 4 pi will cancel here, 1 from here. And we have 1 by r square integration 1 by r square here, 1 by epsilon q square by 4 pi 0 to infinity 1 by r square dr. You know the value for this integration, it is 1 by r. Let me write this is q square by 4 pi epsilon minus 1 by r 0 to infinity. It's like you are founding the energy of this configuration, right? So that is why we are taking over all the space. What is the energy? So that is why we take 0 to infinity. It's actually by definition 1 by r a to b is q square 4 pi epsilon naught minus 1 by r 0 to infinity. Sorry, this should be, there is a minor mistake. This should be b to infinity, right? Because we have already considered the inner region. I think Srishti was talking about that only. Why it was not b to infinity instead of 0 to infinity. Uh, yeah, for the second, it should be from b to infinity. You say by 4 pi epsilon 1 by a minus 1 by b plus q square by 4 pi epsilon b. And if you take q square by 4 pi epsilon common, this will give 1 by a minus 1 by b plus epsilon by epsilon naught b. Recall epsilon by epsilon naught, it is the dielectric constant, which is 1 plus chi e. We can use that. This is q square 8 pi epsilon 1 by a 1 by b plus 1 plus chi e by b. So 1 by b will cancel with one of this value. So we'll get this is energy will be q square by 8 pi epsilon and we have 1 by a plus pi e by b. And you can further simplify it. Epsilon is epsilon naught 1 plus pi b. Okay. So are the steps clear to you? If you have any doubt, feel free to ask. This will be the final answer. So remember the general formula, it's half d dot E, and you are easy to go for finding the energy. Okay, so next we'll start solving the problems related to the Laplacian equation. So this I think it's already been solved in the in the lecture. So there are you need to find out the general solution for Laplacian equation in spherical coordinate and where V only depends on R. So V is only depending on R. So del square V is 0. And if you recall, del square V for the spherical coordinate is 1 by R square, dou by dou R square, dou B by dou R, which is 0. Here we conclude that this should be a constant, and so that is why we have taken V of R is minus C by R plus D. This we have already seen. And the question was asking about give one of the example of this situation. So where did you find this type of potential? If you recall the uniformly charged sphere, the potential is like this. This is one of the example of potential of uniformly charged sphere. In the second case, this is for cylindrical coordinate where you need to find out what is the solution for this when V is only depend on S. For cylindrical, it is 1 by R, dou by dou R of R, dou B by dou R, which is, should be 0. And this should be constant now. And if you take it as a constant, this will be VR is A ln R plus B. And one of the example is the potential of a long wire. Potential term in hydrogen atom. You can take that. It's like our hydrogen atom we are considering it's like a sphere. So you can also take this is one of the example of potential of a hydrogen atom. Yes, if you consider it's a spherically symmetric, then only it's valid. Okay, so let us move to our next problem. So I would like, so for this live session, we'll solve two types of Laplacian equation, which will cover the concept from whatever that has been taught during the weeks. So I won't try to solve many Laplacian equation because it's a long process, so it will take a lot of time. So it's better if you try to solve it in the moment. And I will cover only the parts uh, that will cover all the concept that has been asked in the assignment or the concept that can be applied in any situation. Okay, so one I will try to cover for using the Cartesian one, and other we'll see in the spherical one. So for this question, it's based on the Cartesian system. So there is a cubical box, side of length L. Let me draw it. So you have a cubical box. All sides has length A, and it's given consists of 5 metal plates which are welded together and grounded. So 5 of its surface is welded together and it is grounded. Let us say this fives. The front, back, left, right, and the bottom. These are welded together. And the top is made up of a separate sheet of metal and it is insulated from the others and held at a potential of V0. So this is at V0. So find the potential inside the box. You can see it's a it's, you can use the Laplacian equation and the separation of variable to calculate the potential. So it's a 3D. So dou square by dou x square plus dou square v by dou y square plus dou square v by dou z square should be 0. And the boundary condition is one is v0 when x equal to 0. This plate, and one is v0 when x equal to a, which is this plate. Other is v0 when y 0 and v0 when y equal to a. It is v0 when z equal to 0. And sixth is v0 when, sorry, v is v0 when z equal to a. So the trick is to use the separation of variables. So v, you can write it as x, y, z, x of x, y of y, z of z. And if you put in this Laplacian equation, you will get 1 by x, dou square x, dou x square, 1 by y, dou square y, dou y square, 1 by z, dou square z, dou z square is 0. So the function of x, function of y, function of z. So that means this should be some constant, let us say C1, some constant, let us say C2, and this is some constant, let us say C3. And because all of this sum up, they sum up to 0, so that means one of the constant or two of this constant will have negative sign. So how we can decide which one of these should have the negative sign? So the sign, it depends on the boundary condition. We'll see why the sign is essential, because the sign depends what will be the solution for this double differential equation. If you take a wrong sign, then you will get a wrong result. So to decide which one of this has positive sign and which one of this has negative sign. So if you look at the boundary condition for x, if you see for the boundary, so x equal to 0 and x equal to a, this defines the boundary of this cube in the x direction. And y equal to 0, y equal to a, this is the boundary in the y direction for the cube. And you are seeing at the boundary, the potential should vanish. So this is only possible whenever you have a sinusoidal function, right? So only when you have a sinusoidal function, then you can get the zero values at the boundary. But if you take a positive value here, then for that case, you will get an exponential function which is never zero at the boundary. It can be zero at the uh, one of the plate, but it can't be zero at the other plate. Okay, but generally it is not zero at both of the plates. So that is why for this x and for this y, the sign should be negative. We will get a sinusoidal function. And if we see z equal to 0 and z equal to a, v is 0 at the one of the surface and it is non-zero at the other surface. So that means you you can take a exponential function here. Okay, so that is why we'll take that the C1, C2 as negative term and C3 is positive so that they can add up to 0. So is this clear why I have taken C1 and C2 negative? So this should be, let's say this is some minus k square, y 2 square by dou y square, this is minus l square. So that means 1 by z, dou square z by dou z square, should be k square plus l square. Now the solutions are easy to find out. For x, it should be a sine kappa x, kx or b cos kx. For y, it is c sine ly plus d cos ly. And for z, it is an exponential function. So this will give e to power kx. K is square root of k square plus l square. Kz plus f or let's see e to power minus k square plus l squared z. The constant value will get it from the boundary condition. Let us see one by one. For the first boundary condition, it's given b 0 when x equal to 0. So if you put 0 here, x equal to 0 here, this part is already 0. This will give b. So that means b should be 0. So we have x of x is a sine kx only. There is no b term. If you put the second boundary condition, that is b is 0 when x equal to a. So for that case, if you put x equal to a, this is like k is n pi. So that is why we will see k is n pi by a. Third boundary condition, v is 0 when y is 0. So this will give a similar situation. So d should be 0. So that means y of y is c sine ly. Fourth, v is 0 when y equal to a. So this will give LA is n pi. So that means L is n pi by a. Or let us say this is M. If V0 when Z equal to 0, so this will give E plus G is 0. So that means E is minus G. So Z is e to power square root A square plus N squared Z minus E square root K square plus L square Z, which is nothing but 2 times of A sine hyperbolic function I Z by A square root N square plus L square. So I put the value of K square and L square, which is M pi by A and N pi by A. So the general solution for the potential is XYZ, which is summation of n 1 to infinity, 1 to infinity, Cnm sin n pi x by a sin n pi y by b, sorry, and sin hyperbolic pi z by a square root n square plus n square. Cnm we can get it for using the boundary condition. The last boundary condition is given when z equal to a. When z equal to a, this is V0. So that means we have to put z equal to a here. Cnl sin n pi x by a sin n pi y by a and sin hyperbolic pi square root n square plus n square, which is equal to V0. So to solve it, you can use the trick, that is to multiply integration of two sine function Cnm 0 to a 0 to a sin n pi x by a sin n prime x by a dx, and other is it is 0 to a sin n pi y by a in n prime pi y by a dy. There is a sine hyperbolic function here, sine hyperbolic. This should be equal to 0 to a 0 to a V0 sin n prime pi x by a dx sin n prime pi y by a dy. So this will give a by 2. This will also give a by 2 whenever n equal to n prime. So and m equal to m prime. So that means we have Cnm sin hyperbolic pi square root n square plus n square, which should be equal to 2 by a square V0 duration 0 to a 0 to a sin n pi x by a sin m pi y by b for a dx dy, and this the integration for this is This will give 0, 1, either n or m is even. This we have to remember to save time. And this will give 16 V0 by pi square mm if both are odd. So only odd values will give a non-zero potential. So that is why we have V x y z. It is 16 V0 by pi square. Adjust other expressions in summation of over n, summation over n. N is odd, all odd, m is all odd. 1 by n sin n pi x by a sin n pi y by b and sin hyperbolic y square root n square plus n square z by a. And there is a sin hyperbolic y square root n square plus m square. This will be the final form for the potential after solving the Laplacian equation. So is this clear? So the main step is to find out which one of these, to find out the boundary condition first. Then you need to see which of these boundaries support sinusoidal solution and which one of these follows exponential solution. From that, just use the solution. Then you need to use the tricks to find out the general equation. So is this clear? Okay, so let us move to our next problem. So it's given to derive the expression for P3x using the Rhodesius formula and check that P3 cos theta satisfies the angular equation, which is dou by dou theta sin theta dou theta by dou theta is L plus 1 sin theta theta for L equal to 3. Check that P3 and P1 are orthogonal by explicit integration. Let us solve it. So we have PLX. So recall this is 1 by 2 to power L factorial d by dx L x square minus 1 to power L. So P3x will be 1 by 8 p factorial 6 dq by dx cube x square minus 1 to power whole cube. So 1 by 48. This is easy to find out. This will give, so P3x, if you do the derivative, this will give 5 by 2 x cube minus 3 by 2x. That means P3 cos theta will be half cos theta 5 cos square theta minus 3. So we need to verify this. So if you calculate d3 by d theta, this will give half minus n theta 5 cos square theta minus 3 plus cos theta n cos theta minus n theta. You can take the common of sin theta by 2. This will give 5 cos square theta minus. Okay, so in final, just simplify it, you will get minus 3 by 2 sin theta 5 cos square theta minus 1. This is what we're calculating dou theta by theta. Now we have to take the whole derivative with respect to theta. So that means dou by dou theta of sin theta dp3 by d theta is minus 3 by 2 dy d theta sin square theta 5 cos square theta minus 1. After doing the derivative, you will get minus 3 sin theta cos theta 5 cos square theta minus 1 minus 5 sin square theta. So that means if you divide it by sin theta, you will get minus 3 cos theta 5 cos square theta minus 1 minus 5 sin square theta. Simplify it. So this is 3 cos theta 10 cos square theta minus 6. So we can simplify it to 3 by 2. Let us say 2 cos theta into 2 5 cos square theta minus 3. So this is just to prove that we'll get the right hand side if you take the left hand side. So this is P3 cos theta. And this, when you take L equal to 3, this is nothing but L into L plus 1. So that means it is satisfying the right hand side, L into L plus 1. And I will leave it to you to check whether P3 and P1 are orthogonal or not. Check it. If you are not getting, let me know. Okay. So let us move to our next problem. Please go through the question once. Let me read out the question. There is a volume between two concentric conducting spherical surface of radius A and B. B is greater than A, and this is filled with inhomogeneous dielectric constant. I think it's better if I draw the diagram first. So there is two surface. Inner one is filled with a dielectric, which is epsilon naught 1 plus kr. Epsilon 0 and k are constant. R is the radial coordinate, and d is epsilon r er. A charge Q is placed on the inner surface. Q is placed here while the outer surface is grounded. So outer surface is grounded. So we need to find out what is the electric displacement in the region ARB first. Okay, so let us see one by one. For first one, we need to find D, which is quite easy because the free charge is given. So you can use D dot ds is Q free, which is Q. So because we are considering the region in between this, yes, so Q free is Q. So D dot ds is Q. That means D is Q by 4 pi r square r cube. This is quite easy. Next, you need to find out what is the potential difference between the inner and the outer spherical surface. So for that, you can first calculate the electric field, and from electric field you can calculate what is the potential. And here it's also given d of r is epsilon r e r. So that we know d, so that means e is straightforward to calculate. So e would be d r by epsilon r. So this would be q 4 pi epsilon r square r cube. Epsilon is given, epsilon naught 1 plus kr. You can put it here, so q 1 plus kr r cube 4 pi epsilon naught r square. This is electric field. Now for the potential, you have to take the integration of electric field in the region. So V is minus of PdR, P dot dr from D to A. This would be minus Q by 4 pi epsilon naught. And this is A to B, 1 plus AR by R square dr. So the first integration is integration over 1 by R square, which will give 1 by minus 1 by R, or we can take this minus to inside, so this will be 1 by R from A to B minus AR by R square. This will give ln R, okay, ln R over B to A. So there is a mistake here, so this is B to A. So the potential is Q by 4 pi epsilon naught 1 by A minus 1 by B plus K ln B by A. Potential is done now. Next, we need to calculate what is the surface bound charges at the inner and the outer sphere, which is quite straightforward because we've already solved one of the problem which is similar to this. So surface charge densities P is okay. For that, we need P, right? So D is given. It is epsilon naught, epsilon RE. And D we already know this is nothing but epsilon naught E plus P. which is epsilon V. So P would be epsilon minus epsilon naught E. Epsilon is epsilon naught by 1 plus kr. This is epsilon naught. And E we have calculated. This is Q. This one. So Q 1 plus kr r cube by 4 pi epsilon naught r square. Simplify it further, you will get Q by 4 pi r square and epsilon naught take it inside. This take it inside, you will get this is 1 minus 1 plus Q. So final is Q K by 4 pi r negative sign R K. This is the polarization. Now you can easily guess what will be the surface charge density now. So sigma B for the inner surface, this should be P dot in K for R equal to V, which is minus Kk by 4 pi R vector minus R vector, R equal to A. So this is Qk by 4 pi. Sigma B for the outer surface, B, this should be P dot Nk at R equal to B, which is minus Qk by 4 pi R cube. This is R cube for R equal to B. This should be, okay, this is plus, right? And this will be minus Qk by 4 pi B. This is surface charge density. For volume charge density, what we need the negative of divergence of P, which is 1 by R square, dou by dou R square, Qk by 4 pi R, which is Qk by 4 pi R square. This is all about the bound charge density. For the last option, we need to calculate what is the capacitance of the device. So we know electric field, we know the potential. So if you just divide Q by V, then we can find out what is the capacitance. C is Q by V. So V, we have already calculated it. This one. So this should be 4 pi epsilon naught AB B minus ABK ln B by A. So 11th question. The potential inside a dielectric sphere of radius r and the permittivity epsilon is phi of r theta is a r theta, where a is the constant. Find the bound volume charge density, find the bound surface density. So I think it's quite straightforward because we have already solved few problems related to it. So let me write out the final solution that you will get. Calculate it and check it whether you are getting the same answer. For row B, you will get A epsilon minus epsilon naught 2 theta by R plus 4 theta by R, and sigma B, this would be minus A epsilon minus epsilon naught theta. Check it. Let me know if you have any doubt. Okay, so let us move to our next problem. So there is a electrostatic field in the charge-free region, which is the form V of r theta phi is f of r cos theta. So you need to find out what will be the functional form of f of r. Given you have f of r is this, or this, or this, or this. So there is a charge-free region, so and V is given. It is f of r cos theta. So because it's charge-free, so that means it will follow the Laplacian equation. And for the spherical one, we have 1 by r square, 2 by dou r square, dou v by dou r, plus 1 by r square sin theta, dou by dou theta, sin theta, dou v by dou theta. It should be 0. V is given, so cos theta by r square, dou by dou r square, dou by dou r, plus f of r square sin theta, dou by dou theta, sin theta, dou by dou theta cos theta will be 0. So that means we will simplify it further. This will give 2r dou f by dou r plus r square, dou square f by dou r square, plus f of r squared sin theta, dou by dou theta. Let us take the derivative. This will be minus 1 dou sin theta cos theta will be 0, and the sin theta will cancel. We have cos theta by r squared dou square by dou r square, 2r dou f by dou r minus cos theta by r square, 2f of r, which should be 0. So this will give r square dou square f by dou r square plus 2r dou f by dou r minus 2f of r should be 0. So we can't get a direct solution for this. So the trick is use the options that is given to you and check which one of this option is satisfying this differential equation. Whichever is satisfying this, that will be the solution for this problem. And if you check it, the option B, it satisfies this equation. So that means the f of r should be option B, which is AR plus B by R square. So is it clear? Okay, so let us solve our next problem. It's similar to the Laplacian equation, but in the previous problem we have seen based on the Cartesian coordinate. Here we'll solve it for a spherical coordinate. So it's given the potential at the surface of a sphere of radius A is V0 is K cos theta, where K is the constant. Find out what is the potential inside and outside the sphere, as well as the surface charge density sigma of theta on the surface of the sphere. Assume that there is no charge inside and outside the sphere. So that means it satisfies the Laplacian equation in that region, and we can use the separation of variables. So first, let us simplify V0 first. Let us write V0 in terms of the Legendre polynomial. So V0 K cos, it is K cos 3 theta. If you simplify K cos 3 theta, you will get this is K 4 cos square theta minus 3 cos theta. And if you recall the Legendre polynomial, this is quite similar to the P1 cos theta, and this can be related to the P3 cos theta. So how these are related, we don't know for now being. So for that, what we can do? So let us say V0, you can write it as some K times alpha P3 cos theta and some beta P1 cos theta. We don't know alpha for now being, but if you equate this to this, we can get what is alpha and beta. So left hand side is K 4 cos square theta minus 3 cos theta. Right hand side is K alpha P3 cos theta is 5 by 2 cos q theta minus 3 by 2 cos theta, and beta P1 cos theta is cos theta. Now we can equate the orders of the cos theta. So K will cancel. We have 4 cos square theta minus 3 cos theta is alpha by 2, 5 cos cube theta minus 3 cos theta plus beta cos theta. So this will give 5 alpha by 2 cos q theta plus beta minus 3 alpha by 2 cos theta. So if you equate it, sorry, this will be cos square theta, right? Or am I missing something? Okay, so this will give cos q theta. Now if you equate the order, 5 alpha by 2 it should be 4. So that means alpha is 8 by 5. And beta minus 5 alpha by minus 3 alpha by 2 is minus 3. So this will give, check it once, this will give Delta is minus 3 by 5. So V0 is 3 by 5, 8 P3 cos theta minus 3 P1 cos theta. So the reason we are doing this is that in the next step that we'll see, this simplification will simplify our integration because we know the integration of P3, PL and PL prime cos theta is 2 by 12 plus 1. So we want to use that trick to solve the boundary problems. So that is why we first is the V0 in terms of the Legendre polynomial. So now the general solution for the uh, for a spherical system, if you recall, this is summation L0 to infinity L R to power N PL cos theta for R less than equal to 1. And in the outside, we have L0 to infinity BL R to power L plus 1 PL cos theta for R greater than equal to R. So our task is to equate the boundary condition. So at R equal to capital R, it should be K by 5, sorry, 8 P3 cos theta minus 3 P1 cos theta. So left hand side, we can use summation of L R to power L, PL cos theta, where L is from 0 to infinity. This is equal to this form. So now we'll use the trick summation L 0 to infinity L R to power L 0 to pi L cos theta P L prime cos theta sin theta d theta. And in the right hand side, it is K by 5, 8, 0 to pi P3 cos theta PL cos theta sin theta d theta minus K 0 to pi PL prime, and this is P1 cos theta PL prime cos theta sin theta d theta. Left hand side will give, this is only valid, or this will only give a non-zero integration whenever L is equal to L prime. And the value will be 2 by 2L plus 1. So this will give L R to R L. Summation will, this will vanish. This will be 2 L plus 1. And in the right hand side, we have K by 5, 8. And this integration is only give non-zero value when L prime is 3. So that is why this is 2 by 2L plus 1 delta L3. And the second, this is 3 2L plus 1 delta L1. So only few steps left. We have now, this is AL is 2L plus 1 by 2 to power R to power L, K by 5, 16 by 12 plus 1 delta L3 minus 6 by 12 plus 1 delta L1. Simplified further, it will give A by 5, 8, 12 plus 1 will cancel, L3 minus 3 delta L1. So that means AL, the value of AL is 8K by 5. Okay, so there is a RQ term here. At our L. So 5 at our Q when L equal to 3, or it is minus 3K by 5R when L equal to, otherwise it is 0. So that means V of R theta is now, for the inside we have minus 3K R 5R P1 cos theta plus 8K 5RQ RQ P3 cos theta. Okay, so this is for the inside one. For the outside one, you don't need to calculate what will be B. So we have already calculated the value of AL. So we now equate AL with BLs, and then we can easily calculate what is BL for now. So at R equal to all at the surface, the inner and the outer values should be equal. So that means AL R to RL, AL cos theta should be equal to BL R to RL plus 1, PL cos theta. So that means this will give AL R to RL should be equal to, so this is capital R to RL plus 1. So BL, it is related to AL by AL R to R 2L plus 1. So we have already calculated what is the value of AL. So that is why we don't need to follow the same step for AL now. 3, 5, 1 and L is 1. Or it is otherwise 0. So that means BL, it is 8K R to power 4 by 5 when L equal to 3, or minus 3K R square by 5 when L equal to 1. Otherwise it's 0. So that means just put the value of BL to find out V of R theta for outside. This will give, so I'm writing the final expression that you should get. K by 5, 8 R by R to R 4, 8 cos theta minus 3 R by R square P1 plus theta. Okay, so this is all about the potential. For the surface charge density, if you know, this is related to epsilon naught summation L0 to infinity 2L plus 1 L R to RL minus 1 L cos theta. We know L, we know what is the non-zero value of L. So that is why this would be epsilon naught A1, P1 and 7 A3 R square P3. So I put L equal to 1 here or for other case, I put L equal to 3 plus 2. So A1 we know, A3 also we know, P1, this is nothing but cos theta. So this is 3 minus 3k by 5r cos theta plus 7, 8k by 5r square over cube r square 5 by 2 cos theta minus 3 cos theta. So sigma theta, we should get this is epsilon k cos theta by 5r minus 93 plus 140 cos square theta. So this is one of the problem based on the spherical coordinate. So we do have few more problems to solve it. So, but let us see those problem in our next live session. So for now, let me know whether you have any doubts in any of this problem. Otherwise, we'll stop for now. Okay, so if you don't have any doubts, let us stop for today. Thank you for joining the session. So I hope the problems that I've solved it will be helpful for you to solve the assignment. If you have any doubts, feel free to ask me in the next live session or write it in the discussion forum. We'll meet on next Friday, same time from 6 to 8 to solve few more problems that is related to method of images or the problems that we didn't solve today. So let us meet on next Friday. Thank you for joining this session. For now, goodbye everyone.